Before going on to the video, let me introduce myself to you real quick. Hello, my name is Anshul. I'm an electrical engineer. I like to explore and learn new things. YouTube is the new thing that I'm exploring and learning these days. Apart from this, I like gaming, reading books. Currently, I'm studying and preparing for engineering service examinations, so you guys can expect video of any of these above mentioned things. With no further ado, let's just jump onto the topic.
Ever since the day that you went away, you've been sending flowers to me, flowers today, flowers today.
We know that transfer function of first order system is by taking inverse Laplace transform, we get C of t is equals to 1 of t e raised to minus t upon t u of t. It is inverse Laplace expression of standard first order system. But note, the 1 of t, the 1 upon t, this 1 upon t is amplitude part, not time part here. Most people get confused here. Though its notation is t, its position is amplitude, and hence its feature is amplitude. This confusion should be avoided. It will be clear with the following example. A question was asked in exam. Impulse response IR of a system is equals to 10 e raised to minus 2t u of t. What is time constant? What most people would do is, as c of t is equals to 1 upon t e raised to minus t upon t u of t. 1 upon t is nothing but by comparing both 1 upon t is nothing but 10, therefore t is equals to 1 upon 10. This is completely wrong. Here IR is equals to 10 into e raised to minus 2 upon t u of t. C of t is equals to 1 upon t e raised to minus t 1 upon t u of t. 1 upon t is equals to 2 here. That is, time constant is on the power of e. The 10, it is nothing but amplitude. We want time constant. Time constant is on the power of e. Therefore here 1 upon t is equals to 2. Time constant is equals to 1 upon 2 is equals to 0.5, not 1 upon 10. Therefore note, in c of t, 1 upon t e raised to minus t upon t u of t, 1 upon t, this 1 upon t is amplitude. And this 1 upon t is time. Let's plot this impulse response in graphical form. At t is equals to 0, let amplitude response, say A. It will decay exponentially according to time and will be 0 at t is equals to infinity. This is impulse response or transient response. How can we say from this impulse response if a system is stable or not? If equation is absolutely integrable, that is, area under curve is finite and can be calculated, then we can say that system is stable. That is, if integration 0 to infinity impulse response, mod of impulse response d of t is less than infinity, then stable. What is the use of mod? Why did we apply mod here? Sometimes negative transients may be present while calculating, even if area can't be calculated and is infinite. Due to these negative transients, it may look finite and system will be falsely considered as stable system. Getting back to inverse Laplace transform of standard first order system, C of t is equals to 1 upon t e raised to t minus 1 upon t u of t. This minus 1 upon t is nothing but closed loop poles, where s is equals to plus or minus 1 upon t. Is equals to 1 upon 1 plus s of t. As we know that C of t is equals to 1 upon t e raised to t minus 1 by t u of t. Here s, that is closed loop poles, are minus 1 by t, that is negative, and in the left side. If the closed loop poles are positive, that is plus 1 by t, then the inverse Laplace transform of the standard first order system's transfer function will be C of t is equals to 1 upon t e raised to t plus 1 by t u of t. Its graphical representation will be something like this. And if closed loop poles are 0, that is neither negative neither positive, then C of t will be 1 by t e raised to 0 u of t, and its graphical representation will be something like this. Therefore, we can say that when poles S are negative, area is finite and is integrable and hence stable. When poles are positive or 0, area is not finite and therefore unstable. Therefore, and note this, we can say that for causal LTI system to be stable, closed loop poles should be negative or should lie on LHS of plane. We studied about transients and how, because of them, system is unstable. But why do transients occur in a system? There can be many reasons. Main reason is energy stored in system components. Thus, we relate the graph this way as well. As you can see here, energy is being decayed. Therefore, it may reach to stable at some point. But here energy is not being decayed and therefore unstable system. Now, if we draw tangent to this graph, this tangent represents that energy is being decayed with the initial speed. Transients will be decayed in one time constant. This is what we consider as ideal condition. This tangent is what we consider as an ideal condition. This is what we want. But here, practically, it's not happening. So, what we considered ideally. Thus, it's said this first order system is sluggish or slow. This is also the means through which we practically, in day-to-day life, differentiate if a system is first order system or not. Most of the first order systems are sluggish and slow. If you see a control system and it's kind of sluggish or slow, it's first order system. All temperature control, level control system, water purifiers that we see are first order systems. Here, the slope is minus a upon t. That is, we know that how to find the slope, y2 minus y1 upon x2 minus x1. Ideally, at t, we want transients to die out, but practically at t, only 63% of transients die out, 36% are still present. So how can time constant be defined? I have got 5 definitions. Time constant, as studied earlier, is equals to nothing but RC. Time constant is also the reciprocal of pole value. Time constant is time required for 100% transients to die out, ideally. But practically, time constant is time taken for 63% of transients to die out. That is, first definition is from electric response. Second definition is from transfer function. Third definition is from ideal impulse response. And the next definition is from practical impulse response. Fifth definition we will study in steady state response. Now let's take an example. This is the following graphical representation of impulse response. Calculate the time constant from this. See, this graphical representation is given just for confusion. You need to observe it carefully. The given graphical representation is already ideal. Therefore, you must have thought that 1 is the time constant here But no, and as the given graphical representation is of ideal impulse response, compare it with the graph of ideal impulse response. Here time constant is 2.